The George Mason, yeah. According to my like family lineage, I'm like some descendant of George Mason.
So we lose that.
Exactly. You're losing to my family.
No way we're losing it.
Don't let that be true. I hate those guys.
Okay. So, I know everybody is dying to know, in the new equilibrium we are studying, where particles are being exchanged and with maximized entropy, the rate of change of the entropy with respect to particle number on the two gases must be equal. But what physically does this represent, this equality? Right now, nothing really, but we're going to make it into something. What we're going to do is we're going to take equation 1, and right now, well, we can think about what the units of both sides are. The particle number is dimensionless. So the units of both sides of equation 1 are units of entropy, which is joule per Kelvin. So, dimensions of energy over temperature. Okay, it's not too bad, but that's close to energy. And that's something I can think about, something with dimensions of energy. So, let's multiply both sides by the temperature. Since we're in thermal equilibrium 2, they have the same temperature. So I can multiply both sides by the same temperature. The only thing that, so that's kind of intuitive. The only thing that isn't intuitive is we're also going to multiply by a negative sign. Now that's purely a choice, but it turns out to have been convenient. Okay? So, we're going to multiply equation 1 by negative temperature. Remember they have a common temperature, so we'll just call it negative T. And by the way, while we're at it, let's have a new definition. The new quantity we're going to define, first I'll give you the definition, then I'll give you the name, because the name's going to be kind of weird, and the name is really just a name. So just focus on the definition. Take the negative temperature times the partial derivative of the entropy with respect to the particle number, where everything else that the entropy depends on, tends to be U and V, is held constant. Okay? That's my new quantity. Negative temperature times the partial of entropy with respect to particle number, holding U and V fixed. Again, that's just based on what I just talked about over there in equation 1. Okay? And we'll number this. Now I'm going to give you the name and the symbol for this new quantity. First of all, we know it has dimensions of energy. So you might think we call it something energy. Not quite. Alright, it is called the chemical potential. Its symbol is a lowercase mu. Okay? This is the definition of the chemical potential of any system. Take the negative temperature of the system times the rate of change of its entropy with respect to particle number holding U and V fixed. Okay? By definition, that's the chemical potential of any system. The SI unit of chemical potential is the unit of temperature, Kelvin, times the unit of entropy, joule per Kelvin. It's the joule. So it's got dimensions of energy. And I'm just warning you, it's tricky to think about this thing, but I suppose you could think of it as kind of a new form of potential energy. Kind of in the name, chemical potential. Okay? But it's really kind of like a form of energy. It acts like it. It acts like a form of energy. Okay? So, back to equation 1, we can rewrite equation 1 like this. When we have reached equilibrium, partial derivative of S with respect to N on the two sides will be equal, but just multiply both sides by negative T, which is equal for both, and you really have now determined that the chemical potential of gas A must equal the chemical potential of gas B. And then when this is true, we have reached what is called diffusive equilibrium. Okay? So, if you had a container with the two gases, and you put them into contact initially with this porous wall between them so they could exchange particles. If they start out with values of this thing called chemical potential that aren't equal, because of the chemical potential imbalance, there will be a net transfer of particles from one side to the other until the chemical potentials are equal. Then there will be no more net transfer of particles, and we will have reached what's called diffusive equilibrium. Okay? That's the new aspect of equilibrium we have now, when you can exchange particles between the two systems. So now, let me rewrite the thermodynamic identity. Second time around. This is our second exposure to it. So now I'm supposing that the entropy of our system is a function of the energy, volume, and particle number, and allow energy, volume, and particle number to change. All three. The energy can change by an amount du, the volume can change by an amount dv, and the particle number can change by an amount dn. What is the change in the entropy? So I'm just extending the idea I had before for the thermodynamic identity and including a third variable that can change, n. So the answer is right back to multivariable calculus. My function s is a function of u, v, and n. I have three infinitesimal changes, du, dv, dn. They all can contribute to the change in entropy as follows. ds equals the partial of s with respect to u, holding v and n fixed, times du, plus the partial of s with respect to v, holding u and n fixed, times dv, plus the partial of s with respect to n, holding u and v fixed, times dn. Simply calculus. Okay? Now, what we do is we say, okay, partial of s with respect to u at constant v and n is 1 over the temperature. Partial of s with respect to v at constant u and n is pressure over temperature. Partial of s with respect to n at constant u and v is negative chemical potential over the temperature. And then rearrange and get an expression for du. So du equals T ds minus P dv plus mu dn. And we have the thermodynamic identity. I think we're up to equation. This one up here is equation 3, where the chemical potentials are equal at diffusive equilibrium. And now the enhanced thermodynamic identity is equation 4. It relates the change in energy to the entropy change, the volume change, and the particle number change. Okay? Okay, so we have defined chemical potential as the rate of change of the energy with respect to the particle number times the temperature. That's not, well, that's a bit abstract. Although, that's what we've been doing. We've been doing these partial derivatives. But let's talk a little bit more, so C, about how to interpret this new quantity called chemical potential. Okay? So what I'm going to do is I'm going to do this. Well, first let me show you a spreadsheet. Now this is similar to kinds of spreadsheets you've done several times. Now I'm going to take two Einstein solids. Okay? Let's assume they're already in thermal equilibrium. And I'm not going to let them, or they're not anymore, exchanging energy, because they're in thermal equilibrium. Okay? So I'm going to think of the energy as fixed. QA has 200 energy units and QB has 100 energy units in thermal equilibrium. So that's not going to be changing. But I didn't start out with them in diffusive equilibrium. So I don't have the right number of oscillators between the two. And I'm going to assume that they can exchange oscillators. Now we haven't thought about that before, but if you put two solids in contact, and you just wait long enough, atoms will eventually, from random motion, cross over. Okay? Now I'm going to think about oscillators as my particles, but I'm going to just say that they can exchange particles, oscillators. Okay? And that what's fixed is the total number of oscillators, 100. So in my table, this column is not Q sub A, like we have been doing when they exchange energy, but N sub A, the number of oscillators in solid A. Then of course N sub B is 100 minus N sub A. So it's just like what you've done before, but we're not doing QA and QB. We're doing NA and NB, okay? Just go with it. Yes?
Is there a reason why you don't have the 0, like, NA is 0 and NB is 0?
No, I'm allowing for all possibilities. See, this column's going to go down. NA, oh, you mean why I'm not doing 0?
Yeah.
No, I just didn't. For some reason, I guess I was in a hurry, I didn't start with it. But you're right, it could be. Yes, it could be. I just probably got in a hurry. Okay? Okay, so you understand what I'm saying? It's just like before, but instead of QA and QB, it's NA and NB. But you can still calculate the multiplicity for each, yes? It's the same multiplicity function. So you can calculate the multiplicity for solid A based on NA and QA. And therefore its entropy over KB by taking the log of the multiplicity. Yes? And you can do the same thing for solid B. You can do its multiplicity based on NB and QB. And then did SB over KB by taking the log. So far, just like before. And then you can do the total multiplicity by doing the product of the two multiplicities. And then the total entropy by the logarithm of the total multiplicity. Yes? With me? Now I've got a new column, two new columns. The chemical potential for Einstein solid A divided by KT, and the chemical potential for Einstein solid B divided by KT. They have the same T, remember. How did I get that in the spreadsheet? Well, I divided both sides. I divided both sides of this by T and a KB. So what I really need is the partial of S over KB with respect to N. Well, I did that by a finite difference, like you've done before. All right, I took the change in S over KB over the change in N. So to get this mu A, like right here, I took that S minus that S over that N minus that N. With a minus sign, don't forget the minus sign. You understand what I'm saying? So I just did finite difference approximation for that derivative, and I can calculate the chemical potential divided by KT for solid A, given the NA, and for solid B, given the NB. And then I can go and I can make plots of the entropy of each solid versus NA. And the total entropy for the system combined versus NA. And I want to show you, and I also plotted the chemical potential for A and the chemical potential for B versus NA. And I want to show you what those graphs look like. They should look somewhat similar, at least the top ones. Entropy over KB versus NA. Solid A's in red, solid B's in green. As NA increases, the entropy of A increases, but the entropy of B decreases. And when you add those two, you get the curve in blue, which is the total entropy. And for a particular value of NA, you get a maximum in the entropy, the total entropy, yes? That's going to be equilibrium value of NA. You might be able to guess what that equilibrium value of NA is. Look at the energy quantum, 2 to 1, right? When we're in thermal equilibrium, turns out that the correct number of oscillators for A to B is 2 to 1. So that turns out to be basically 66, 67. For NA at equilibrium, that's where that peak is. So we know S total is maximized for this value of Na, and that has to correspond to equal chemical potentials. So, let's plot that. Chemical potential over Kt versus Na. Red curve is solid A, green curve is solid B. Look what happens at the equilibrium value of Na. They cross. They're equal. Where the chemical potentials are equal is where the entropy total is a maximum. And you are at what's called diffusive equilibrium. And when you're at diffusive equilibrium, there'll be no net transfer of particles one way or the other. They'll still be going back and forth, but they'll be going in equal amounts. And there'll be no net transfer. But what if you're far away from equilibrium? What if oscillator A has way too few, solid A, has way too few oscillators compared to solid B? That would put you down, say, here. Now look at this entropy curves. Remember how we looked at this before when we plotted versus QA? Now it's just versus Na. Look at solid A's slope on the entropy graph. Steeper than solid B's. So if we're down in here on the Na axis, solid A wants to gain oscillators so as to increase its entropy. Yes? Solid B will end up losing oscillators and will end up losing entropy, but it won't lose as much entropy as solid A gains. And the net effect is S total will go up if Na goes up. That if you're down here. So if you're over here, far from equilibrium, the net direction of particle transfer is going to be from B to A. From B to A. So as to make the entropy bigger. Down here, I've drawn this arrow to show the way the particles diffuse. From B to A. From the chemical potential on the green curve towards the chemical potential on the red curve. From B to A. That's the way the particles are going to want to go if you're down here. Now, if you're over here above N at equilibrium, then solid A has too many oscillators. And this curve is steeper than that one. So now, solid A wants to lose oscillators, and solid B wants to gain them. And that will still make the total entropy go up. You'll go this way now, and you're still going towards the P. So if you're over here, the direction of particle diffusion is from A to B. And notice something. Whether you're below equilibrium over here to the left or above equilibrium to the right, the direction of particle diffusion is always from the solid with the larger chemical potential to the solid with the smaller chemical or lesser chemical potential. From the solid with the larger chemical potential to the solid with the lesser chemical potential. Even if both chemical potentials are negative. Okay? So that's the big upshot. This is the takeaway message. Particles tend to diffuse toward values of lower chemical potential. Just like systems naturally want to minimize, go to lower potential energy, like a piece of chalk. If I let go, it's going to naturally move down and lower its gravitational potential energy. Okay? Okay, so how do you interpret the potential energy, chemical potential? It's this. Particles diffuse from regions of higher chemical potential to regions of lower chemical potential. So, from higher to lower. Okay? That will continue. The particle diffusion will continue until you have the same chemical potential everywhere. Then there's nothing driving this diffusive transport of particles. Diffusion, by the way, is a kind of motion where the atoms more or less move randomly, but yet still end up kind of spreading out or distributing something. In this case, they're kind of distributing chemical potential until it's everywhere even. Okay? But if you have a difference in chemical potential, that will drive diffusion. Okay? Now let me show you another way to calculate chemical potential from the thermodynamic identity, the new form, equation 4. Okay. So, back to the thermodynamic identity, equation 4. First of all, you can play the game like we did before, where you take some quantities in the thermodynamic identity and you set them equal to 0, and then you see what's left. So you can see that, for example, if you have a situation where du is equal to 0 and dv is equal to 0, no energy change, no volume change, equation 4 becomes negative T ds equals mu dn, which you can then rearrange, and you get the definition of chemical potential. So if you don't have to memorize the definition of chemical potential, you just have to memorize equation 4, the thermodynamic identity. And then by setting du and dv to 0, you reproduce the definition of chemical potential. But let me consider another possibility. What if we have a situation where ds is equal to 0 and dv is equal to 0? No entropy change, no volume change. So these two terms, here and here, are equal to 0. How does equation 4 simplify? Well, it becomes pretty simple. du equals mu dn, which you can rearrange and get mu equals the partial of u with respect to n at constant s and v. And we have another way to calculate chemical potential, or another way to think about it. It's the rate of change of the total energy with particle number, if the entropy and the volume don't change. Okay? Now it's sometimes useful, at least to think about what chemical potential is telling you about a system. It's sometimes useful to write this derivative in a somewhat funky looking way. But let me remind you of something I said a little while ago. The smallest change in n that you could have is 1. We're not going to divide up particles into fractions. Okay? So the simplest, I suppose you could say, way to write that rate of change of u with respect to n is as a finite u with a delta n equal to 1. Where I think of the numerator, so the denominator is just a 1. The numerator is the change in the energy when the particle number, let's say, increases by 1. But s and v don't change. So that's u as a function of s, v, and n plus 1, minus u as a function of s, v, and n. I just changed the particle number by 1. I did not change the entropy. I did not change the volume. That's a way to think about this derivative, as a delta u over delta n. And so I can think of it as I can think of chemical potential as the rate of change of the internal energy with respect to particle number if you don't change the entropy in the volume. Okay? My thesis advisor used to always say the chemical potential is, I think, a little bit loose. But he would say, oh, the chemical potential is the energy you have to provide to put another particle in. That was his kind of quick and dirty way to describe it. Well, it's the change in the energy of the system when you add a particle if you don't change the entropy or anything else that the energy might depend on. Okay? Let me give you a little toy example of this. It's quite a toy example. It's not the most realistic thing, but it gives you some feel for chemical potential. Let's consider an Einstein solid with a trivially simple number of parts, 3 oscillators, and 3 energy quanta. So the total energy is 3 times epsilon, where epsilon is the quantum of energy, of oscillation. Right? So the total energy U is Q times epsilon, where Q is 3. Let's figure out what the multiplicity is, because we know how to do that. If n is 3 and Q is 3, it's Q plus n minus 1 factorial, it'd be 5 factorial, over Q factorial n minus 1 factorial. So 5 factorial over 3 factorial, 2 factorial is 10. So the entropy is KB log 10. Fine. Okay, now I'm trying to get a feel for what the chemical potential of this Einstein solid, toy version of an Einstein solid will be. So I'm going to think of it as the change in the internal energy if I increase the particle number by 1 over 1. Okay? That's how I'm going to think about it. But I have to make sure that when I add another particle, go up by 1 particle, I don't change the entropy. I'm not going to worry about the volume because the Einstein solid has no volume dependence. But I do have to worry about the fact that the entropy can't change when I add this particle. Because if I just try to add a particle, I would go from 3 oscillators to 4. And if I didn't change anything else, when I went from n equals 3 to n equals 4, wouldn't that make the multiplicity go up? Because this would then be 4 comma 3. 4 oscillators, 3 quanta. Then this would be a 6. And a 4 and a 2. Right? And that number turns out to be 20. So the entropy would go from KB log 10 to KB log 20. Well, it increased. Yes? Well, that's not what mu means. Mu means change the energy. What is the change in the energy? When you change n by 1, but don't change s. You with me? So I can't just add a particle. I have to do something else also so that the entropy doesn't go up. Do you see what you could do? What other thing can you change while you add your particle so that the entropy doesn't go up? Yeah. And specifically the Q. What am I going to have to do to it, you think? I don't want it, I only have 2 possibilities. Q can either go up or it can go down. Right? So what do you think I want to do? I think that'll make the entropy even bigger. Go down. Okay? So when I add the n to go up to 4 oscillators, I must at the same time take out a Q. Then I'll be at 4 for n and 2 for Q. That'll have the same multiplicity. And I won't have changed the entropy. Okay? Alright, so to increase the particle number by 1, without increasing the entropy, I must at the same time take 1 unit of energy out. So the way my thesis advisor would say, he said, well, it's the amount of energy you have to add to put another particle in. Well, but this is going to be negative, meaning it's, in this case, it's the amount of energy you have to take out to put another particle in. Okay? All right, so increase n to 4 and decrease Q to 2. Then the multiplicity is 5 factorial over 2 factorial, 4 factorial, 3 factorial, which is still 10. And so the entropy is KB log 10, and that's unchanged. So with that in mind, now I have an estimate for the chemical potential of the Einstein solid. It's going to be the change in U over the change in n. The change in n is 1. I'm adding 1 oscillator. I'm going from n equals 3 to n equals 4. How much did the total energy of the oscillator change by? 1 quantum, yes? Out. 1 quantum going out. So that must be minus epsilon. So the chemical potential is minus epsilon. Negative. Because you have to take energy out. If you don't want the entropy to go up when you add a particle. Okay? you will find that it's quite common for classical systems, like the ideal gas, to have negative values of chemical potential. Because generally speaking, when you add a particle to a classical system, if you don't want the entropy to go up, you must take energy out. Okay? All right, let me give you another example. How about the monatomic ideal gas? How about calculating the chemical potential for it? You start with the entropy using the soccer tetrode equation, which I will remind you looks like this. For a monatomic ideal gas, the entropy is NKB times 5/2 plus natural logarithm of the volume per particle times 4 pi the mass of an atom, the total energy U, over 3NH squared, that part's raised to the 3/2. Right, that's the soccer tetrode equation for the entropy of a monatomic ideal gas. And that's where we're going to start. And we're going to use the definition of chemical potential. I'm not going to go through the steps of the math. Okay? So, the chemical potential of the monatomic ideal gas is negative T times the partial of S with respect to N, holding U and V fixed. Okay? Well, I'm going to let you do that partial derivative. You do the partial of this with respect to N. Okay, you got to do the product rule, the chain rule, all that fun stuff. And then multiply by a negative T. I'll tell you what you get so that you can check yourself. You get negative kBT times the natural log of the volume per particle times 2 pi mass of an atom, kBT, over h squared, and that part is raised to the 3/2. This equation, as far as I know, does not have its own name, like the entropy equation does for a monatomic ideal gas. But this is the chemical potential of a monatomic ideal gas. Maybe you ought to get some numbers at least to get a feeling for this. How about for helium? At room temperature, 300 Kelvin, and atmospheric pressure, 1.01 times 10 to the 5th pascals. Right? Helium, as an ideal gas at room temperature, atmospheric pressure, you can just use the ideal gas law to get the volume per particle from the temperature and the pressure. You get 4.14 times 10 to the negative 26 meters cubed per atom. You can think of this volume per atom, or the inverse of the particle density, where the particle density would be the number of atoms per unit volume. And by the way, you know enough chemistry to figure out the mass of a single helium atom. You take the molar mass of helium divided by Avogadro's number, and you get 6.65 times 10 to the negative 27 kilograms. So you plug in numbers here. Okay? I'm going to do it in steps. You get the chemical potential is negative kBT. We'll put in the T in a minute. Times, let me tell you what you get from just figuring out the logarithm part. First of all, the log itself is dimensionless. The units of the chemical potential come from the kBT out front. And the dimensionless factor of the logarithm is a positive value to 3 sig figs at 12.7. That's just from the logarithm. Positive from the logarithm. So the chemical potential is definitely going to be a negative quantity. Now I'm going to express it in electron volts for the energy instead of joules, so that's just more usable. There's used kB in terms of electron volts per Kelvin. and then multiply by T of 300 Kelvin, and you get negative 0.328 electron volts. Okay? And you can do all kinds of fun things with this. One of the things that your author talks about doing is plotting the chemical potential of the gas at a fixed temperature as a function of particle density, N over V, with particle density increasing to the right. Okay? And he discovers when he plots that, that it's just an increasing function. The chemical potential is always negative, but it's getting less, or sorry, it's getting more, it's going towards zero. Right? So as I increase the particle density, if the chemical potential is getting larger, that means the gas is more willing to give up particles. Because particles diffuse from higher chemical potential to lower. So if I put that gas in contact with another gas with a lower chemical potential, the one with the higher chemical potential is going to have some of its atoms diffuse over. Okay? So if you put the gas in a situation where its chemical potential goes up as you change some variable, that means you're making the gas more want to give up some of its particles. Remember, chemical potential is basically a measure for the tendency of the particles to diffuse from one place to another. They diffuse from where the mu is bigger to where the mu is smaller. And diffusion continues until the mu is the same everywhere. So let me close today by doing a problem out of your author's book. With some practice on chemical potential. It's number 37 in chapter 3. And it says, consider a monatomic ideal gas that lives at a height z above sea level, so that each molecule has gravitational potential energy mgz in addition to its kinetic energy. Okay? Calculate the chemical potential for this gas, in this case, using the definition mu equals negative t, partial of s with respect to n, and constant u and v. Okay? So how are we to do this? Well, let's imagine that we have a container with a monatomic ideal gas. Just some box, okay? And that gas is at a height z above sea level, okay? And we'll just take 1z to describe it. Maybe the box is rather short and wide, okay? Just 1z to describe the box. And the gas has some volume, some temperature, and some number of atoms, okay? Monatomic ideal gas inside that box, okay? We are to calculate the chemical potential, starting with the entropy and differentiating with respect to n. Well, the only entropy we know for the monatomic ideal gas is the Soccer-Tetrode equation, right? So we clearly are going to go to the Soccer-Tetrode equation. But before we do, maybe we ought to be aware of the limitations or the restrictions that were placed on it over here. Okay? We got to remember how we got to this. We got to this by assuming that the only contribution to this symbol, which we call the total energy, or we call it the internal energy. We're somewhat sloppy in what we called it. But the total contribution to that was from the fact that the atoms were zipping around inside the container, i.e. kinetic energy. Okay? So what we really ought to do, okay, so at sea level, the total energy is all kinetic energy. And that we ought to say for S at Z equals 0, V and N. Okay? Well, I'm going to use K for kinetic energy, V and N. That we ought to rewrite the expression, NKV, 5/2 plus the natural log of the volume per particle times 4 pi m times the kinetic energy, the total kinetic energy of all the atoms in the box, over 3nh squared, all to the 3/2. Right? So I'm going to use the symbol kinetic energy, K. Okay? Instead of U. That's what we've had, that's what we've got right now. Okay? But what do we have? Okay, that's at sea level. But what's going on at altitude Z? Above sea level, or Z level. Okay? Well, what is the total energy of each atom? Well, it's got kinetic energy, but it's also got gravitational potential energy of mgz. Okay? So the total energy of the gas, is, and that's the symbol we mean by U. The total energy is the kinetic energy of the atoms plus the total gravitational potential energy. I have n atoms. They each have mass m multiplied by g and multiplied by the altitude c. Right? That's now the total energy of the gas. So how am I going to express the entropy using the total energy, U, and the altitude, Z? Well, all I have to do is use equation 1 and substitute. Now look, I'm just going to rearrange this. K equals U minus mgz. So I'll use the result above. Oh, this is equation 1. Okay. I'll use that equation right up there for the entropy at sea level, but I'll replace K with U minus N mgz, just from this expression right here. And then I will get the entropy at altitude Z in terms of the total energy and the volume and the number of atoms. And you get this expression. NKB times 5/2 plus the natural log of the volume per particle times 4 pi m parentheses U minus n mgz all over 3nh squared. That parts to the 3/2. This is equation 2. Now I've expressed the entropy as a function of the total energy, the number of atoms, the volume, and the altitude, Z. And now all I have to do to get the chemical potential is say mu equals negative T times the partial of S with respect to N, holding everything else that S depends on except N constant. So that would be Z, U, and V, constant. Well, that's a lot of fun, doing that derivative. So I won't steal that away from you by doing it here. Okay? But I will tell you what you get when you do that derivative. Okay? And it's worth pausing a moment to try to think a little bit or predict a little bit what you should get. Okay? All you've done is take the box of gas from sea level and lift it up to a certain height, yes? So maybe you ought to have the chemical potential here. This is for an ideal gas at sea level. Okay? There was no altitude to worry about. This was an ideal gas at sea level. So it's probably going to be that plus some more. Because you're going to have to supply more energy, yes? To put an atom in now, it's up here. Okay? And in fact, it's quite simple. It's the chemical potential at sea level, the result right over there. Okay? Plus mgz. But we got at it honestly. What do I mean? I mean, you got to go back to equation 2, and you've got to go through there, and you've got to do the partial of s with respect to n. And you've got to do every single step of it. You got a factor of n here, you got a factor of n here, you got a factor of n here, you got a factor of n here. And you got to go through and you got to do that derivative honestly. Doing it all step by step and carefully, and then multiplying by a negative t. And then after you do all that and the dust settles and you get that result, and you say, aha, it is just the value you would have had at sea level plus the extra potential energy they have now because they're at height z per atom. Yes? mgz. Because you've got to bring that much more energy now to the box to put an atom in. So you might, if you really, really were forced, if I put you in a corner and I said, now wait a minute, think about this a little bit. What do you really think you're going to get physically? I probably would have been able to get you to this answer just by talking physically about it. But you also need to be able to show how if you do all this honestly, that is what comes out. Okay? It's just the extra gravitational potential energy you got to put in. Now there's just one more part I'll talk you through. Suppose you have two chunks of helium gas. One at sea level and one at height z. Each having the same temperature and volume. Assuming that they are in diffusive equilibrium, find a relationship between the number of atoms at height z, n of z, and the number of atoms at sea level, n of 0. So imagine a setup like this. In part B, 2 containers with a little pipe connecting them. They have equal volumes, and the gases inside have equal temperatures. Okay? That little connector lets them exchange particles. This box is at z equals 0. This box is at altitude z. Okay? This gas will have some number of particles n, but it'll depend on z, it turns out. And this gas will have some number of particles, so it'll be n of 0. And you just leave it like this. Just leave it. You don't do anything special. Make sure their temperatures don't change on you. But this little connector lets them exchange particles, okay, atoms. And just wait. And they will come to diffusive equilibrium. And we know that means their chemical potentials are equal, right? So the chemical potential for the gas at height z must equal the chemical potential for the gas at height 0. Okay? So I should add one more thing over here. This one has a chemical potential mu for altitude z, and this one has a chemical potential mu for altitude 0. But I have just waited a long time and let them exchange particles as they will. And if I wait long enough, they'll reach diffusive equilibrium where the chemical potentials are equal. Okay? So I'm going to use my result over here for the chemical potential. Let's number that equation 3. All right? We use equation 3, and we set mu I've written it in terms of T, Z, V, and N of Z must equal mu of T, 0, V, and N of 0. So here on the left, I just use equation 3 directly. Okay? You just use equation 3 directly. And then you set that equal to, on the right, you go in and everywhere where there's a z, you put it to 0. There. And then you say, well, the n is for the n of the lower box, so n of 0. Okay? So it looks like this. Negative kBt log of v over n of z times 2 pi m kBt over h squared to the 3/2 plus mgz must equal. Right? That's the left side. Must equal mu at z equals 0. So negative kBt log of v over n of 0, 2 pi m kBt over h squared to 3/2 plus 0. And what you can do is you can solve that equation, because you've got a lot of things that are the same. Same temperature, same volume. Right? A lot of things cancel out of that, and you can solve for the number of atoms in the box at altitude z. And I will just write down what you get. The number of atoms in the box at altitude z is equal to the number of atoms in the box at altitude 0 times a negative exponential, negative mgz over kBt. i.e., n at height z is less than n at the ground level. It's exponentially decaying, right? We actually did a problem in chapter 1 where we saw that the density and the pressure of the atmosphere decays exponentially as you go up. This is the same thing. We just came at it from a completely different angle of attack, okay? So, in order to come to diffusive equilibrium where the chemical potentials are the same here and here, you have to end up having more particles down here than up here. Surprise, surprise. Okay? And if you start out with equal numbers of particles here and here, which may be something pretty easy to imagine, the tendency for diffusion will be a net direction downward. Because this gas will have a larger chemical potential than this one, initially. And particles diffuse from larger chemical potential to smaller, or higher to lower. Okay? So if you start out with equal number of particles here and here, this one's definitely going to have a higher chemical potential than that one. And so the net direction of transfer is going to be down. Okay? But the net transfer will stop once the chemical potentials are equal and the number of atoms in the two boxes are related by this function. Okay. So that brings me to the end of chapter 3. So now you have time to study, to gather your thoughts, to come to me if questions arise as you're studying. Okay? Trying to get all these ideas put together in your head. Yes? Yes, chapter 3. Not a huge amount though, but a little bit.
Okay, so like the main ideas?
Yeah.
Okay.
Yeah.
I'm going to need to
Spreadsheets, no. Mathematica might be handy, spreadsheet will not be necessary.
So if that being said, you want us to grab
Possibly.
functions?
You may have to plot a function, but you should be able to do that in mathematics.